All right, so in this section of Unit 3, we're going to focus around potential energy. All right, and so just remember that this is also kind of that physical science definition. Right, so energy that is stored for later use is known as potential energy. Right, and if you remember from middle school science, right, that's essentially the definition that you're given. Right, and so stored, right, and so basically what really happens is any force. Okay, the majority of the forces that we talk about do have potential energies associated with them. The two big ones that we're going to look at here are going to be what is known as gravitational potential energy, potential energy, which we call U sub G. And then the second one is going to be elastic potential energy, okay, which is going to be U sub S. The reason why I call it U sub S because this is going to be the spring force, right? So, and then this will be essentially the weight, right, or the gravitational pull, right? And so one thing to know is that these are two what we call conservative forces, and all conservative forces do have potential energies associated with them. Okay? So first, let's dive into gravitational potential energy. So gravitational potential energy is the amount of work required to move it, let me say an object, right, from one location to another, okay? And so the equation is just going to be simply U sub G equals mgh, right? And so if you want to break this equation down, right, mgh, well, and we're talking about how this is a work, right? mg is F sub G, so that's a force, and H is a special distance. So notice that we're just multiplying force times distance with this equation, okay? Just like every other energy, the unit is going to be joules, okay? And at this point in time, that's all it is for gravitational potential energy. So let's take a look at a couple example problems. So here you have find the gravitational potential energy of a 65 kilogram person sitting on a diving board that is 3 meters high. And so all we're going to do is plug in our values, right? So U sub G equals mgh. So we're going to use 65, we'll use 10 for simplicity, times 3. And so you do 65 times 10 times 3, you find that the person sitting on top has 1,950 joules of energy stored, okay? We'll get into conservation energy in a little bit, and if that person now jumps off the diving board, this potential energy will be converted into kinetic energy, okay? But that's when we're going to talk about conservation of energy here very shortly, all right? The next one, a candy bar called the Mountain Bar has a nutritional energy content of 8.87 times 10 to the 5th joules. So if an 81 kilogram mountain climber eats a mountain bar, it converts all of its energy to potential energy. What altitude gain can the climber achieve? So this kind of goes back, so we wonder why we count calories. There is a joule to calorie conversion. And so this is what happens, right, when we eat food. All that energy in the food, right, all the calories, we're going to convert it to other forms of energy, okay? And so we start with our equation, U sub G equals mgh, all right? And we're going to solve this equation for H. So all we're simply going to do is just divide by mg. So U sub G equals, or H equals U sub G over mg. And so it's going to be 8.87 times 10 to the 5th joules divided by 81 times 10. Okay? And so when you do that, you're going to find that they can climb 1,095 meters, okay? Which is short of a mile. If Quest asked you to convert this to miles, you would just say 1 mile, right, 1,609 meters, which I didn't do that calculation on the sheet, but if we do that, it's going to be 1095 divided by 1609. It's about 0.68 miles, right? So just under 3/4 of a mile. Okay. All right. Now, this is not the only potential energy that we're going to account for here. Okay. The next one is the one associated with springs and rubber bands. And so we refer to this as elastic, or springs and rubber bands are referred to as elastic because they return to their original size and shape after being distorted. Now, again, this is a conservative force, right? This is the Hooke's law we talked about. Okay. So we talked about Hooke's law before. And we talked about springs, back and forces. So the potential energy stored in a distorted elastic material, right, is called elastic potential energy. Okay. Sometimes you'll see it abbreviated as U sub E. I just use U sub S because most of the situations we'll talk about will be for springs. Okay. Now, when a spring with the force constant K is stretched or compressed by a distance x, the amount of work done on the spring is equal to 1/2 kx squared. Now, this is also the spring potential energy equation. They're the same thing, right? Because when you stretch a spring, you're giving it potential energy, okay? And you're doing work on the spring. Now, the work is stored as elastic potential energy, all right? So when you stretch that spring, you're giving it this elastic potential energy, and then when you release it, then it gets converted into other forms of energy, gravitational potential energy, kinetic energy. Okay. All right. Now let's just look at a couple of equations with this. So this says that a spring with a spring constant of 120 newtons per meter is compressed a distance of 2.3 centimeters. How much potential energy is stored in the spring? So we're going to use our basic equation. So 1/2 kx squared. So we're going to do 1/2 times 120. Now you do have to be careful because this is in centimeters and our K is in meters. So you need to make sure that these are in the same unit. So we're going to do 0.023 meters, and we're going to square that. I'm just going to confirm my answer. 0.5 times 120 times 0.023 squared gives us an answer of 0.0317 joules. Okay. Now notice this spring, right, doesn't store a lot, right? But if you take like a garage door spring, right, that's going to store a lot because your K value is going to be much higher, right? And that's why garage door springs tend to are very dangerous if they ever break. Okay. Okay, so this next problem is going to talk about it takes 200 joules of energy to compress a 1 meter long spring to 70 centimeters. How much work would it take to compress the same spring from 70 to 50 centimeters? Okay. One thing that you can think about is this: is that this is our 0 point, right? And so this is going to be 0.3 meters, right? And so our stretching or compressing is going to be 0.30 meters, okay? And so the thing that we're missing for this spring is the spring constant, okay? We can't do the second half, we can't actually answer the question until we figure out what K is. And so what we're going to say is we're going to say US is 1/2 kx squared. And we're going to solve this for K. So it's going to be 2US over x squared, right? So 2 times the potential energy divided by that compressing or stretching distance squared. So it's going to be 2 times 200 joules divided by 0.30 squared. So it's going to give us a K value of 4,400 newtons per meter. Okay, so now we have the K value. Now we can tackle the actual question. Okay, so one thing to remember, we're trying to find the energy to stretch it to from 0.7 to compress it really from 0.7 to 0.5. We got to find what is the potential energy at both positions. So we're going to do kx, 1/2 kx final squared minus 1/2 kx initial squared. Now you can clean this up to help you put into your calculator a little bit by just saying 1/2 k All right, it's like I'm going to factor out that 1/2 k, 1/2 k, okay, to be 1/2 k times x final squared minus x initial squared. But you do also, again, have to be careful. These are in centimeters, and we need them in meters. Okay, so just divide everything by 100. So you're going to do 1/2 k, which you found to be 4,400 newtons per meter. Okay, and then our final position is going to be, really, you could pick either one. So we're going to 0.70 squared minus 0.5 squared. And it's going to tell us it's going to take 528 joules to do that. So a couple things you can notice that sometimes with these questions, what they'll do is they'll make this difference the same, okay? But understanding that you have to, the reason why we could just call this 0.3 for our first situation is because we said, okay, this here is our 0 point. And so our initial, position would be 0, so that we're only left with that 1/2 kx squared part, okay? And so remember, a spring force is a variable force. It's going to take more force to get it to stretch further, right? As you keep stretching, it's going to get it to, you need more to stretch it, okay? Which is the reason why you have to put more energy into it, all right? Okay, and then from here on out, we're going to talk about conservation of energy. We'll look at power. We'll look at energy pie charts. And we'll just keep finishing this chapter.